What if the 2.3 million blocks used to build the Great Pyramid of Giza were not quarried, but were actually cast? This is the controversial theory proposed by Joseph Davidovits, who argues that many of the pyramid stones were made from an ancient geopolymer, an early form of synthetic concrete. Chemical analysis of pyramid blocks reveals air bubbles trapped inside the stone, something that should not exist in natural limestone. Even more striking, human hair fiber had been found trapped inside some blocks, implying the material was still wet when it was placed. Further laboratory tests identified chemical compounds and amorphous silica phases that do not occur in natural limestone, but are consistent with low-temperature man-made stone. According to Davidovits, ancient Egyptians dissolved soft limestone using water and alkaline solutions, poured the mixture into molds which hardened into stone, allowing the precise fittings of the stone where a sheet of paper can't even pass between the gaps, suggesting the pyramids may represent one of the earliest examples of advanced material science in human history. If this is true, this still makes the builders of the pyramids far more advanced than history is ready to accept. We continue to support our theory, which we have discussed numerous times on our channel, that the pyramids are not tombs, but sophisticated structures built by a civilization far predating the dynastic Egyptians, and that they are far older than the conventional dates repeated in history books. But in the context of the geopolymer theory, we're going to view it as it's presented by Davidovits, who believe the pyramids were built by the Egyptians as we know them. This approach allows us to examine the evidence without redefining all of Egyptian history at once. It also helps show that even within the standard historical framework, something extraordinary may have taken place. Another disclaimer we'd like to point out is that the large-scale casting animations we'll show you are not very accurate. According to the theory, the blocks were molded directly in place where they were supposed to fit, in three-sided wooden molds that are connected to the already finished blocks, as shown in this animation, which is correct. Due to the limitations of AI technology, we couldn't generate this exact process on the large-scale animations, but we hope you understand the theory. Joseph Davidovits did not begin his career as an Egyptologist, but as a chemist specializing in synthetic mineral materials and industrial binders. While studying ancient monuments in the 1970s, he became interested in Egypt after noticing that some pyramid stones behave differently from natural limestone under chemical testing. His background in polymer chemistry led him to examine pyramid blocks with analytical techniques rarely used by archaeologists at the time. When he obtained a small sample of a casing stone from the Great Pyramid, the so-called Lauer sample, and examined it under a microscope, he observed telltale signs of artificial composition. Not only tiny trapped air bubbles and organic fibers, but even bits of animal bone and teeth embedded in the material, foreign inclusions that would never be present in normal limestone formed over millions of years. Such features are exactly what one expects in man-made concrete, where organic fibers like straw could be added for tensile strength, and air bubbles get trapped during mixing. And their presence in a pyramid block provided the first material indication that these stones were cast by ancient builders rather than purely quarried. Though this idea initially seemed far-fetched to many, it becomes more plausible considering the materials and chemical know-how available to the ancient Egyptians. They had abundant limestone, of course, but also access to key reagents like natron, a natural soda ash, from dry lake beds and limestone-derived quicklime, as well as various clays from the Nile floodplain. Egyptian craftsmen were already adept at sophisticated mineral-based technologies. For example, they produced a self-glazing ceramic called faience by mixing silica, quartz sand, with lime and natron, which, if left unfired, can actually self-cement into a hard, stone-like substance over time. In fact, the ingredients needed to cast pyramid blocks, powdered limestone, a clay or kaolin binder, alkalis like natron, sodium carbonate, and lime, were all readily available in Old Kingdom Egypt, meaning the pharaoh's builders had the raw materials to create a type of concrete long before the Romans perfected their lime and volcanic ash mortar. Additional geological clues soon emerged from the pyramid blocks, particularly regarding the fossils naturally present in Giza limestone. The bulk of the pyramid was built using nummulitic limestone, a rock peppered with fossilized shells of ancient sea creatures from when Egypt was covered by an ocean eons ago. In untouched sedimentary rock, such fossil shells lie in neat horizontal layers as they were originally deposited, but within the Great Pyramid stones, the fossils are jumbled in disarray, oriented at random angles. This messy pattern is exactly what you would expect if the limestone had first been crushed and then reformed. When shells and fossil fragments are mixed into a wet, muddy paste and poured into a mold, they settle in random directions instead of lining up in neat layers. The cast block theory also offers elegant solutions to some long-standing puzzles about the pyramid's construction. One such mystery is the extraordinary precision with which many blocks fit together. In places, the stones are joined so perfectly that not even a human hair can be inserted between them. A level of accuracy that could be naturally achieved if semi-liquid stone were poured and set directly against the neighboring block's surface. Likewise, despite the pyramids containing millions of dressed stone blocks, archaeologists have not unearthed large numbers of copper chisels or pounding tools at Giza, even though the conventional theory assumes extensive quarrying and carving of stone, and copper is a soft metal that would have worn out rapidly and been discarded in great quantities. If instead many blocks were cast in place, the need for armies of chiseling stonecutters and vast quantities of metal tools would have been dramatically reduced, which aligns with the archaeological silence on evidence of such tools. Reimagining the building of the pyramids in this way sheds new light on how the ancient Egyptians could accomplish such a colossal project. Rather than tens of thousands of laborers dragging 2.5-ton blocks up long earthen ramps, much of the work could have been done by relatively small teams of workers mixing and casting blocks in situ. This method would eliminate the need to haul giant stones to great heights. Instead, crews could carry baskets of damp limestone mush and buckets of reactive binders up the pyramid as it rose, and there pour fresh blocks right where they were needed. Such a process is inherently well suited to achieving the pyramid's celebrated precision. Because each new block could be cast against the ones around it, it would mold itself perfectly to its neighbors, curing into a snug fit and thereby accounting for the incredibly tight seams. Not only does this scenario answer practical questions, like how the highest levels of the Great Pyramid were built without massive ramps, but it also portrays the project as less about brute manpower and more about clever engineering, making the pyramid as much a triumph of ancient chemistry as of civil engineering. To demonstrate that the method was practical and not just theoretical, Davidovits and his team recreated the production of re-agglomerated limestone using exactly the natural materials that would have been available to the ancient Egyptians 4,500 years ago. All steps of the work, from mixing, carrying the buckets, to compacting the material into wooden molds, were performed entirely by hand, exactly as it would have been possible in ancient Egypt. The results were identical to those shown at the Great Pyramid, and the joints of the blocks were also perfect. Nevertheless, there were still many gaps in the geopolymer theory of Davidovits. For example, there are an estimated 500 to 800 granite blocks in total inside the Great Pyramid, some of which weigh up to 80 tons. Granite blocks cannot be geopolymer cast. Davidovits accepts that the granite blocks used in the pyramid were quarried and transported from Aswan, and states that they were reserved for load-bearing and relieving chambers, as well as structural beams. He argues that they do not invalidate the geopolymer casting of limestone. A major practical challenge is scaling the geopolymer process. Casting millions of blocks would require enormous quantities of water, binders, molds, and controlled mixing operations. Critics question whether Old Kingdom Egypt had the logistical infrastructure to manage such a chemically intensive process on that scale. No remains of large-scale mixing facilities, mold yards, or production waste have been identified at Giza. The lack of direct archaeological evidence is a serious weakness. No molds, mixing basins, geopolymer residues, or written instructions describing stone casting have been found. Given how well documented other Egyptian technologies were, this absence is striking. Critics argue that a technique this revolutionary would have left clearer physical or textual traces. Moreover, if the pyramids were built with geopolymer, why not use the same method for all the other grand Egyptian temples and structures, all of which are hand-carved? There is also the problem of construction speed. While casting might seem faster than quarrying, geopolymer stone requires curing time. Scaling this process to millions of blocks without bottlenecks is difficult to model realistically. Critics argue that traditional quarrying with organized labor may actually be more efficient. One of the biggest gaps in the geopolymer theory is that the majority of pyramid blocks closely match the natural limestone of the Giza Plateau in composition, texture, and fossil structure. Many geologists who have examined large numbers of blocks report that their mineralogy, grain boundaries, and sedimentary features are consistent with quarried stone, meaning a small fraction of the blocks could be cast geopolymer. Another concern is tool mark evidence. Many pyramid blocks show chisel marks consistent with stone cutting. Casting would produce smooth surfaces that require no finishing. Critics argue that the widespread presence of tool marks supports traditional carving methods. Perhaps the truth is somewhere in the middle. That's what a materials scientist, Michael Barsoom, stated when he published a pivotal study in 2006, proving that, although not all, at least some of the limestone blocks were made with geopolymer. When scientists looked at the stones under powerful microscopes, Michel Barsoom noticed something unusual. The tiny particles inside the stone were glued together by a binding material that does not exist in natural limestone. He found silicon-rich material, likely from sand or clay, mixed very closely with limestone minerals like calcium and magnesium. In nature, these materials do not combine in this way. The structure shows they were mixed in liquid form and then hardened quickly. This is supported by the fact that the binding material looks disordered and glass-like. Natural limestone forms slowly over millions of years and has neat, well-ordered crystal structures. The pyramid stones do not show this. Instead, they look like modern concrete, which hardens quickly from a wet mixture rather than forming slowly in layers. Barsoom also discovered that the pyramid stones contain much more water than normal Egyptian limestone. Natural limestone from the Giza Plateau is dry. Man-made stone, however, traps water during mixing and hardening. Even more telling, minerals inside the pyramid blocks were found in a hydrated form, something that does not happen in natural limestone, but does happen when minerals form quickly from water. Salt inside the pyramid stones provides another important clue. Normally, limestone from ancient seabeds contains very little salt, and any remaining salt would wash away over thousands of years. However, salt has been found inside the pyramid since ancient times. Historical accounts say that when the Great Pyramid was entered in the 9th century, its passages were coated in salt crystals. Salt can still be detected in the stones today. This suggests salt was mixed directly into the stone itself. Even studies of Earth's magnetic field provide clues. Some pyramid blocks show magnetic alignment consistent with being cast in place while hardening. Nearby blocks show random alignment, as expected from stones that were cut and moved. This suggests the builders used both natural stone and cast blocks, especially higher up where lifting heavy stones would have been difficult. After carefully examining the geopolymer theory, we can conclude that at least some portion of the construction was made through geopolymer techniques. We as researchers continue to support our belief that the pyramids are far older than conventional archaeology claims, that they served far more sophisticated and technological purposes than mere tombs, and that their origins predate dynastic Egypt entirely. Perhaps this is why nowhere else in Egypt do we see the same geopolymer methods being used. The pyramids appear not as the beginning of Egyptian civilization, but as inherited structures adapted and reused by later dynastic cultures. In this view, the Egyptians did not originate the pyramids, but preserved, modified, and ritualized monuments that already existed. We discussed this in detail in one of our previous documentaries on the pre-Egyptian antediluvian civilization, where we examined the true origin of some of the most sophisticated structures in Egypt, so make sure to watch it. Long before recorded history, there were advanced ancient civilizations capable of building gigantic megalithic structures we can't build today. Lifting enormous stone blocks weighing thousands of tons and stacking them with laser-like precision. Blocks we still struggle to lift even with our modern cranes. They crafted mathematically precise, flawless monuments from the hardest stone on Earth, leaving us to wonder who these builders were and how they accomplished the impossible. Were they merely primitive societies, or were they masters of a forgotten technology lost to the sands of time? Uncover the evidence of an ancient, global, and technologically sophisticated civilization that once ruled over our planet, constructing gigantic sites the ruins of which are still standing, before a cataclysmic event erased it from memory. Access our ebook, Prehistoric Megastructures, a nearly 500-page volume packed with images and in-depth analysis of some of the most astonishing and unexplained ancient structures ever discovered, monuments that were clearly built with advanced technology from a time long forgotten. There's a limited discount on the ebook, so make sure to get yours before it's too late.